Well, thank you for that kind introduction and challenge. I don't know up to the challenge. Let me get this working. Okay, there we go. Well, it's a pleasure to be here. Thanks for the invitation to be able to present here to the Blue Water Symposium. I've been a fan user involved with NCSA for a very long time. And today I'd like to talk about some of the issues that arise when going to Exascale. And I'm going to do that using the example of dense linear algebra software. So I haven't said the word yet. And it covers a lot of ground. So basically this is a story of what I've been doing for the last 43 years. All right, so that's the ground we're going to be covering. The outline is something like, you know, where have we been before, what the current situation is, and some of the challenges and plans as we head towards exascale computing, and again, through the eyes of that kind of software. So the software I'm talking about solves very common problems in linear algebra. So this is solving systems of linear equations, least squares problems, singular value decomposition, eigenvalue problems, dealing really with dense problems. So not sparse, not iterative methods, but really focusing on this set of problems. But I want to go back in time, and I want to look at what was happening back in the early 70s. So in the early 70s, we were just starting to understand about performance and some of the issues that portability could bring. And one of the first things that sort of crystallized that was these things called the level 1 basic linear algebra subprograms, the BLAS, but the level 1 BLAS in particular. So now let's see, my batteries are not working very well. The situation here is there was a paper published that looked at these BLAS back in 1973, trying to identify what were the critical routines that were used in linear algebra and trying to propose a standard for the implementation of those routines with the idea of allowing for portability as well as for performance in this regard. So the level 1 BLAS were created to help with just those two things. This is the list of authors who helped with that. About that time, this project was starting. And the computers that were being used were things like a Cray 1. So that was the high performance machine of its time. VAX 11780s were also in common use within groups or universities to effectively carry out large-scale scientific computing. As a result of that project, I became an accidental benchmarker. And if you take a look at the appendix to this user's guide, Appendix B, you would see a list of the first benchmark report, and that the origins of that are from 1977. This is the group of people who put together LinPack. Oops, I said the word. Yeah, we'll have to drink that. So this is Jim Bunch, that's Pete Stewart, this is Cleve Moeller, and this is a 1977 version of me with a little bit more hair, and this is my car, as you can see the license plate there. So these are all, the three guys here were sort of famous linear algebra numerical analysts. Cleve, you may know Cleve the best. He's the guy who gave us MATLAB. So he's the originator of that effort. And he used this software in developing MATLAB initially. This is the benchmark report that appears in Appendix B. So that's the collection of 20 machines I had, roughly. High performance machines from a Cray 1 down to a DEC KA10, a PDP system down there, looking at solving a system of linear equations. The matrix was of size 100 because I could fit that in all of these machines, and I recorded the time to solve the problem. And that scribble, that pencil scribble, is the megaflop rate that it produced. So the highest one was this NCAR Cray 1 with 14 megaflops in 1977. So that was quite impressive. That was a long time ago. So here's a MATLAB trivia question. If you're a MATLAB user, what does the function Dongarra do? So there's a function in MATLAB which bears my name, and if you put Dongarra of some value, you'll get an answer. The question is, what is it doing? And this is that group of people, the four of us, a couple of years ago, looking a little bit whiter, a little bit less hair, and maybe a little bit wider as well. So that's sort of the early story. That software was developed around the level 1 BLAS, these vector operations. So the way things worked for a standard decomposition that took place for these matrices in preparation for solving the ultimate problem was basically to look at a column of a matrix, try to introduce zeros in the column, and then apply the transformations that were used to introduce those zeros to the rest of the matrix, doing a vector operation across that. And that has a number of issues associated with it. One is it does bulk synchronous kind of processing. It does operations which changes a tremendous amount of data. A lot of data is communicated or moved during this operation, much more than really needs to be. And the process goes from a single thread of execution to something which could be done in parallel down to a single thread again. And that's sort of the bulk synchronous processing. That's a loop level parallelism, I'll say. And that kind of parallelism, well, maybe back in the 70s was okay, maybe in the 80s, you can't do that today. That's going to kill you in terms of performance, and we'll see examples of that. In the late 80s, we realized that in order to get performance on the machines that were available, machines that had cache architectures, machines that focused on trying to get reuse of data, we had to do better than just simple vector operations, which sort of updated a large amount of data. And we created a set of standards, the level 2 and the level 3 BLAS, matrix vector and matrix operations were standardized in terms of the calling sequence, again to allow for portability as well as for performance. And these cache-based systems were coming in place as well as small SMP machines. And the algorithms that were designed changed the model of just doing one column at a time to basically going off on the side and looking at what you need to do to transform a set of columns, a panel of columns, and introduce zeros into them. So think of it as going off on the side, doing what's necessary to introduce zeros in that panel, and then applying it to the rest of the matrix. And if you do that, you can cast that operation in terms of a higher level BLAS routine, in terms of a matrix routine. And in particular, the matrix routine is doing this operation here. We've got this red rectangle and this red rectangle that are multiplied together to update this green square block of the matrix. And it was through that we can extract a tremendous amount of performance, getting reuse of data. We have an operation which is roughly order n cubed operations with order n squared data movement. And that surface to volume effect lets us get at lets us reuse data in cache and lets us get very high performance on machines. So basically, we restructured all of the routines in that previous package and organized things to effectively use this kind of block partition algorithms to get high performance on these machines. And that was pretty well. That did pretty well. So that went on. That operation took place in the early 90s. NCSA, I guess, had its early beginnings in 1985 with a proposal that was written to NSF for funding a bunch of centers. And just to put things into context, MPI was created around 1991. We used it in our packages. This is the group that did ScaLAPACK. Myself and Jim Demmel were the primary architects for that package. And of course, we had a large number of people who helped preparing that package, developing the software, and putting it into place for what it is today. That's my car again. It has a slightly different license plate. This time it says ScaLAPACK, and I guess I could say that word. Okay. And it was about this time when distributed memory machines were starting to be put in place. So machines that did explicit message passing, we had a standard for doing that now with MPI, and we thought about taking that package and doing something with it. So here's a trivia question from ScaLAPACK. That's the ScaLAPACK matrix, and the trivia question is, what's the inverse of it? So symbolically, when I multiply that matrix by its inverse, I get the identity matrix. What is that inverse matrix? Okay, so LAPACK is a package. We reformulated the algorithms, tried to look at using these level 3 BLAS to get high performance. Nearly all the things going from linear systems of equations you can reorganize in just that way. Singular values and eigenvalue problems, symmetric eigenvalue problems. You get about half of the algorithm in terms of matrix-matrix. The others do matrix vector operations. And we're going to see that, division between half of the work being done in matrix vector can kill the performance on modern architectures. It really drives it to 2 orders of magnitude less than what you might expect. Non-symmetric eigenvalue problems, you get about 80% using those level 3 BLAS operations. So that was the LAPACK package. It's still in use today. It's in wide use. It's distributed. It's picked up by vendors. It's available. It's still maintained. NSF has provided us with a grant to carry on the software through an SSI grant, and that's still quite extensively used in the community. We transitioned to ScaLAPACK, as I mentioned. Distributed memory machines were coming into place, and we wanted to take those algorithms and make them work in that setting, but we wanted to be able to maintain the software. Writing code at the MPI level is really like writing an assembly language for these kind of algorithms, and we wanted to avoid doing that. We realized that we wanted to maintain this code over decades, basically, and we couldn't do that by writing at the MPI level. As soon as the programmers who implemented something at that level left, it was a mystery exactly how the code functioned. So we had to raise the level of granularity and do that through a software layer that we called the parallel BLAS. The parallel BLAS operated at the global space of the matrix. It understood how the data was distributed across the ensemble of processors, and through that understanding, the parallel BLAS then were able to encapsulate the message passing that went on. So it was able to determine if it had to send and receive between processes, what kind of data it was responsible for sending or for receiving, and then the operations that were required to go on. So that was a level of granularity that allowed us to express the algorithms at a very high level, allowed somebody to write code, and allowed that code to be turned over to the next generation of people who were maintaining it with the understanding that they could actually understand the code and carry on either fixing bugs or improving the overall performance of that. There's some performance issues with the way that was designed, however. The major problem with ScaLAPACK, I'll say, is the lack of overlapping communication and computation. Those 2 phases were kept separate. So the computation was done, and then we went into a mode where everything was communicated. So we did a lot of communication across the whole machine, and then we went back into a phase of doing computation. And that's going to kill the performance. And what we see today on the systems that we have as we go to tens, hundreds of thousands of processes, up to millions of processes, that software that we have really doesn't scale the way we wanted it to because of that reason. So we get no overlap, and we see this tremendous performance hit taking place. So the codes need to be reorganized in some sense to allow for that overlap of communication and computation to break that bulk synchronous kind of processing that goes on with the communication and computation phases. And that's what we're currently looking at. So a lot has changed since those 2 packages were created. We have an experimental package we call Plasma that really looks at many-core and trying to implement those algorithms very efficiently on a many-core system, as well as a package called Magma. Again, an experimental package trying to focus on accelerators and designing the code that would effectively use that level of the architecture to extract as much performance as we possibly can. I'll say those are experimental packages. What we really need to do is to encapsulate both of those ideas in Plasma and Magma in the next generation of software. So just to refresh this, this is the parallelism we extract from LAPACK. We do this block partition algorithms, which works on parts of it. We get a lot of parallelism at certain components, but then there's a synchronization point. So we get this parallelism, synchronization that occurs over and over again within the algorithm. We really have to change that. That synchronization point is going to ultimately kill the performance on any large-scale machine. And just to show you a cartoon of it, again, we're going to be introducing zeros in this green triangle, and then we apply that set of transformations across the rest of the matrix. We can extract a lot of parallelism with that. So in terms of a graph, we do something sequential, then we do something in parallel, and then we do something sequential again. And that carries on for each phase of the algorithm. That's that bulk synchronous processing. If we take a look at what happens on a 16-core system, let's say, this is a cartoon, if you will, of a 16-core machine looking at how active those 16 processes are throughout the course of the computation. So time is evolving. We have 16 cores here. If a core does something productive in terms of the factorization, it's lit up as a color. If it's not, if it's idle, waiting for something to happen, it's white. So you see a lot of white space in this particular cartoon of doing this. So we want to change that. We want to reduce as much as we can that white space. So if you take a look at this algorithm here, it basically does that operation, then moves on to the next step of the operation and does that as things progress. Well, we'd like to be in a situation of basically unrolling this algorithm and unrolling it so that as soon as we can, we start on the second step of the algorithm, even before the first step is completed, and carry that on as much as we can. So as soon as we can get started on the next step, we want to initiate that, almost preparing ourselves for that next step by doing certain things in a certain order to allow that kind of overlap, that kind of event-driven multitasking to take place within the algorithm. And that leads to an organization which is a little bit different than what we had with ScaLAPACK. Instead of dealing with these rectangles, we're going to decompose the matrix into what we call tiles. And those tiles will then help us in unraveling the algorithm and allowing us to do many more things in an asynchronous fashion, allowing things to take place in almost an overlap way. And that leads to basically a directed acyclic graph of the computation where the nodes in the graph represent operations that are going to be done, and the arcs represent dependencies between them, data dependencies that are between them. So we end up, instead of having this bulk synchronous processing loop level kind of parallelism, we end up with a directed acyclic graph. In this case, this is a Cholesky factorization of a directed acyclic graph. Instead of getting a profile for the execution that looks something like this, when we execute this directed acyclic graph, where we allow for more parallelism, we allow for more things to be done simultaneously, we want to see these graphs being as wide as possible, and that will expose more parallelism associated with it. So we can squeeze out the white space in this particular case, allowing us to do more overlap, allowing those loops basically to be done in an asynchronous fashion, still respecting the data dependencies associated with it, and allowing for the algorithm to effectively be done in a much more efficient way. So we're involved in a DOE project called the Exascale Computing Project, ECP, and that's a project to look at developing what's needed for the next generation for exascale systems. And we're developing software for linear algebra targeting exascale. So that's the SLATE project that's going to take the ideas from plasma and magma and introduce them in a way to build out, to scale out, looking for things to run efficiently as possible, looking for things to scale to large numbers of processes, being able to effectively utilize what's available in those exascale machines, having reliability, error bounds, and all the things that were encapsulated with the ScaLAPACK software, looking at portability across different vendors' versions of those exascale machines, looking for flexibility to construct new routines, and allowing for the kinds of ease of use that we have seen or strived for in ScaLAPACK and ScaLAPACK. Just a few words about the DOE Exascale project. ECP project. So this is a project that has a holistic view of developing exascale computing. It thinks about applications. It thinks about what software is necessary to do an implementation for the applications and the algorithms expressed there. It has the ability to initiate new hardware efforts that would be built into the underlying exascale system, and then ultimately developing that exascale system. This is a 7-year project. It just started this year, and the idea is to deploy an exascale machine in the year 2021. That would be, quote, an advanced architecture exascale machine, and then a follow-on machine in the year 2022 that would be a capable exascale system. And we can discuss offline maybe what those two words mean, but the definition that they're using for exascale is a machine that's 50 times the performance of today's 20 petaflop systems, such as the Titan system at Oak Ridge, a machine that uses somewhere between 20 and 30 megawatts of power. The machine at Oak Ridge is probably on the order of 10 to 15 megawatts. One perceived fault per week is the requirement, one perceived fault in the application running on a machine per week. That's a pretty tough one, I think, to accommodate, and to have software that supports a broad range of applications. So ECP is trying to develop machines for applications, and there's a whole list of applications that are being targeted, and develop software tools which will enable those applications to effectively run across those systems. DOE is not the only one, or the US is not the only one involved in exascale. In China, there's an effort to develop an exascale system, and they have put a stake in the ground and said they will have their exascale system in the year 2020. So that's a year before the US. In fact, they have 3 projects that are being worked on today to develop a prototype system. So there's a machine in Wuxi, which is the #1 machine in the world, the machine that has over 10 million processors in the machine, executing at peak performance of 125 petaflops. That's a machine that's was put in place last year. There's going to be a follow-on to it. So they've designed their own chip. That's a totally Chinese machine. They've designed their own instruction set processor. They've done the fabrication of that, and they've put it in place inside of that architecture. So they have one chip with 260 cores. It's an interesting architecture, an interesting design point for it. We can discuss that offline if you want, but that's interesting thing. The second machine is from the National University for Defense Technology. That's a place in Chencha, which has developed high-performance machines for China for a number of years. They have the Tianhe 2A that they're developing. The Tianhe 2 is in place today. That's based on Intel parts, and there was a big issue with the Department of Commerce about 2 years ago forbidding Intel to sell Intel parts to certain centers in China, and they were one of the centers that they could not acquire Chinese parts or could not acquire Intel parts. As a result, they're building their own processor, an ARM-based system which has their own accelerator which will be used on it to get to high levels of execution. They're expected to have that machine up and running sometime by the end of this year, I believe, is the expectation for that, 100 petaflop version of that machine. And then there's a machine that's coming from Sugun. Sugun is a manufacturer, an integrator, if you will, in China, together with the Chinese Academy. They're going to put together a machine based on x86 architecture. So they have an arrangement with AMD, to take x86 instruction set and use it within a Chinese machine. So it'll be interesting to see how that plays out. That'll be another way to get in. So those are 3 machines being developed. Anything but from the US is the major call from the Chinese side to put in place exascale. There are also efforts within the European community to put together an exascale system. They're claiming they're going to have a peak machine of exascale in the year 2021. It's going to be based on maybe ARM processors, maybe some US components. Price is the initiator there, and there's some cost associated with the development of that system. Japan also has an effort to put in place a sustainable exascale system that looks like it's going to occur sometime around 2023 or 24 in terms of that. So those are the 4 major efforts. These are the 2 guys who are competing right now to put a machine in place. China looks like it'll get there a little bit before the US in terms of deployment of an exascale system. Okay, returning back to this problem of designing software that can be effectively used on those kind of machines, the ScaLAPACK software here basically took an algorithm and dealt with this panel-based partitioning and did operations on it, the fork join kind of parallelism. Today, within the scope of the SLATE project, we're looking at taking that and changing its form so we deal with tiles, having many more operations that can be done, allowing for greater overlap and allowing for greater parallelism to occur within the algorithm. So this is an example of a Cholesky factorization. This is running on a Knights Landing, 68 cores. We're looking at the performance here, so this is gigaflops, different size of matrices, looking at the ScaLAPACK code, so that's the code from the last century for linear algebra, looking at its performance when doing a good job of implementing the underlying kernels using MKL's version of that. This is the Intel version of their software running on their machine, and this is our new software that we're designing that would effectively take care of reducing the overhead, trying to minimize the loop level parallelism, trying to focus on this DAG-based arrangement. And this is the performance graph we get out of those 68 cores, again trying to squeeze out as much as possible that white space or dead area within the algorithm. That's on a matrix of size 10,000. If we increase the matrix to size 20,000, we end up with something which really does a pretty good job of reducing the amount of wasted area there, and we get pretty high performance overall. We've implemented this on a number of processors. This is looking at a 96 core ARM system that we have access to at Oak Ridge National Lab, and looking at the performance for this kind of algorithm. This is the algorithm that we're designing. This is for an LU factorization of a matrix. This is based on the ScaLAPACK software, and this red line here is something that Cray provides with their LibSci version for the ARM processor. And clearly they're doing things in the old-fashioned way. They're not able to get the kind of performance that we see based on this restructuring the code, trying to get at this high levels of parallelism. In the context of developing numerical libraries, you are often in a situation where you need to put together more than one routine to solve a problem. In this case here, we're looking at solving finding the variance covariance of a matrix. So we have a symmetric positive definite matrix. We want to find the explicit inverse of that matrix in computing that variance covariance matrix, and 3 routines are called to do that. The first routine factors the matrix. The second routine will invert one of those factors, and the third routine multiplies that inverse together to compute the explicit inverse. So we see 3 distinct parts. We look at the performance of that. There's a directed acyclic graph for each of those parts. Within the context of the library, we're able to take those 3 routines and basically merge them together in some sense, allowing those graphs to overlap and to interact so that the dependencies from one can affect the dependencies in the second one without having to have that explicit boundary between routines. And when we do that, we end up with a directed acyclic graph for those 3 routines, which looks something like this, and a performance profile which, again, tries to squeeze out that white space associated with shutting down the algorithm or starting the algorithm up, and allowing for much more efficient implementation and effective computation of that. So that's what these directed acyclic graph algorithms buys you in some sense. Going to distributed memory, we want to encapsulate things again, so we have the opportunity for transitioning software from one generation of implementers to the next. That will be requiring us to have a runtime system which will take information, given the way the data is decomposed, figure out what should be done in terms of sending and receiving of that information. So we have a data flow expression of the algorithm. The runtime system is going to be responsible for understanding the data distribution and also understanding how data should be communicated and taken care of in that context. Right now, we're looking at a number of runtime systems. There's a runtime system out of France from INRIA. The guys in Bordeaux have something called StarPU, which looks quite attractive. There's a runtime system that we're developing at the University of Tennessee called Parsec. Guys at Stanford have something called Legion. There's a number of runtime systems that are being developed today, to be honest, and they're all being looked at in the context of how effectively can they be used in the context of our libraries and being able to drive the computations. What we envision in terms of an exascale node is something like this, where we have an exascale node that's made up of 2 kinds of cores. Let me call them lightweight and heavyweight cores, fat cores and thin cores, if you will, and being able to carry out the computation across that node. There'll be DRAM, of course. There perhaps would be NVRAM for allowing data to be stored for perhaps checkpointing. There'll be 3-dimensional stack memory for low capacity, high bandwidth arrangements associated with that. And it's the responsibility of that runtime system to effectively monitor and to use the resources that are there in terms of exploiting the overall computations. If you stare at the Chinese processor, the processor that's in the Shenwei, the #1 machine, it looks a lot like this architecture, where we have fat nodes which really control the story and push things off to an accelerator in those thin nodes to do the computation. Then, of course, there's a question of how you effectively program that at that level, but this is what we would envision for our Exascale node. The features that we see in the Slate project occur something like this. There's a runtime system that's there. We interface to that runtime system. We're thinking of using OpenMP within the node and then going to MPI, of course, to do communication. And the runtime system is the guy that's going to be monitoring that and taking care of that overall. We have a number of things in consideration for that. These have these tiled algorithms that can effectively be used. We have a data distribution, which is very similar to what we had in ScaLAPACK. We use this task-based parallelism where we can extract performance with plasma, and we're able to use accelerators through the ideas that were developed in the Magma project and doing that through the course of using this runtime system. I want to turn to the Intel processor. We know that it's quite a powerful processor today, but just looking at what they've done and what effectively we can do to use that in our computations. Back in the early days of Xeon processors, that processor did 2 floating point operations per core. So those are 64-bit floating point operations, adds and multiplies in the early days. When the Halaman-Westmere came out, they doubled that to 4 floating point operations per cycle per core. So that's what was being completed every cycle, 4 floating point operations. Sandy Bridge and Ivy Bridge gave us 8 floating point operations per cycle per core of that chip. If you go to 32-bit arithmetic, that doubles. So you get twice as many flops out of your thing with 32 bits, but let's say we're interested in 64 bits. Haswell and Broadwell doubled it again. These are small vector operations that are being performed in the processor to effectively give us that kind of data rates or performance. In Skylake and in Knight's Landing, they've doubled that again. So we see 32 floating point operations per cycle per core. So Knight's Landing has 68 cores. So that's a tremendous amount of floating point capable in that one chip. Right, so you've got 68 times 32 flops per cycle can be completed. So I would say that the chips that we have today are really over-provisioned for floating point. Right, it's hard for us to really keep up to feed it to effectively get those kind of rates of execution. And we'll take a look at what that really means. So this is a Knight's Landing processor. We're going to be looking at performance for Knight's Landing and trying to look at what we could do to extract more performance for less power associated with the chip itself. So the chip nominally runs at 215 watts. That's the thermal design power for this particular chip. 68 cores associated with it. It has this high-speed memory, this MCDRAM, which can be used in a number of ways. It could be used as a cache. It could be used as primary memory to your system. It has 16 gigabytes of data associated with it. It has a transfer rate into the processors of 425 gigabytes per second. And then there's the standard DRAM, the DDR4 memory that's associated with this device. It has a large amount of capacity there. Its response rate, though, is about 4 times less. We're about 90 gigabytes per second moving data through that system. So if we can use this part of the architecture, we're of course going to get much better performance associated with the underlying computation. Knight's Landing, if you take a look at the 3 basic operations that we're building our libraries around, that's matrix, matrix, matrix vector, and vector operations. This is the characteristics we see out of using those 68 cores. So for a matrix-matrix operation, we see the performance for a very well-implemented matrix multiply coming from Intel rising up to around 200 gigaflops, so 2 teraflops for a matrix multiply for large matrices. For matrix vector operations, however, we see performance that's around 85 gigaflops, so really a drop in performance there. So that's because of data movement. If you move data, push data around in that machine, it can't keep up with it. We've got those 68 cores, each one wanting to run at 32 flops per cycle. It just doesn't have enough bandwidth to satisfy that kind of operation. There's very little reuse of data doing a matrix vector operation. We read in the matrix, we do our vector operation with it, and we don't get to reuse that matrix reading again. Where matrix multiply, we have this surface to volume effect, n cubed operations, n squared data movement. We can leverage that in this high-speed memory to get our operation counts up. For doing vector operations, we see a drop again because of the nature of moving data around in the system, even into a greater amount. So that's the story of how that chip looks in terms of potential. Remember I said earlier, for some of the algorithms we have, we can drive them fully at matrix levels, so that's good. We can get this kind of performance. But some of the algorithms, we can only get half of them for matrix vector, and the other half are being fired up at matrix vector operations. So the performance drops precipitously for those algorithms because of that matrix vector characterization of the algorithm itself. And to be honest, unless we reformulate the algorithm, there's no way around that on this particular implementation. So we're going to be looking at that processor, and we're going to be using PAPI. So PAPI is a tool that we've developed to help us monitor what's going on inside the processor. Think of it as a way to look at the counters that are available in the processor and do it in a portable way so a programmer can make a call to PAPI and try to understand what the cache miss rate is, or the floating point operation count is, or the number of cycles that have been expended are, and do it in a very portable way. And we've just extended that to look at some of the power issues associated with these processors, in particular power capping. So PAPI has the ability to set the power limit for a processor, not at 215 watts, but even at a lower amount, and then look at the performance that we get when we reduce essentially the frequency of that processor and allowing that processor to carry out the operations. And that's in place today and available, so the latest PowerPoint power cap components are there, allowing us to do this measurement of not only reading, but also setting the power levels that are in the machine. And the objective here is to get energy savings. Ultimately, the objective would be to have a way to automatically do this. So as your program runs, it may be in a position to decrease the frequency or the power cap on the machine to allow for less energy use and still get the same kind of performance out of it. So that's in the nature of auto-tuning and trying to do that in an automatic way, driving, in some sense, this energy savings of the underlying computation. If we take a look at a matrix vector operation, so this is a matrix vector operation where the data is in MCDRAM. So we're going to be looking at two models here. Data in MCDRAM, the fast memory of the chip, and memory that's out in DRAM. We're going to be looking at the comparison between those two. Remember, there's a factor of 4 in terms of the data transfer. On a Knight's Landing, you could set it up so that MCDRAM is the primary memory, and that's where all your data is stored, in that 16 gigabytes of data. So this is what we see out of PAPI. This is looking at a number of things from PAPI. We just have the nominal frequency voltage set for this particular thing. The maximum power limit is here at 260 watts. We see the performance from an idle state jumping up in terms of the power consumption for a matrix operation. It jumps up to around 240 watts, and then at 240 watts, during the operation, the thermal design power is reached, and the processor automatically decreases the power going into the chip. The chip is getting too hot at this point. We're using the computationally intensive parts of it, and that heats up the chip, and the response by the processor is to reduce the power consumption down to this point. And the processor does this transparently to the user, and the computation proceeds until the end. So this particular run gave us about 2 teraflops of performance out of this. It consumed, it was able to get an efficiency of 8 gigaflops per watt. So 8 gigaflops per watt is the efficiency that it was reaching for that particular implementation. And now what I'm going to do is to ask PAPI to decrease the maximum power for the chip. It was set up here at 260 initially, and I'm going to ask PAPI to reduce it. And when I ask PAPI to reduce it down to 220, I get slightly different behavior for matrix vector. This thermal power thing doesn't cut in at this point. The processor runs at the power level throughout the course of it. And this is what we see in terms of the power usage. In terms of the performance, it's almost the same. We get a little bit drop in performance at 220 watts, and we see a slight increase in terms of the efficiency. The flops per watt actually goes up in this particular case. And if we decrease it by another 20 watts, we see a drop in terms of the power being consumed, of course, and the performance reacts. The performance drops again, and we see a power efficiency about the same as we did before in terms of flops per watt out of it. So we're reducing the power, but we're getting a better efficiency out of this overall thing. The performance in terms of the amount of floating point operations per second is going down, but the effective use of that is increasing. And if we do that through the course, reducing the power being given to the processor, we see things go down in a very standard way. The frequency associated with that drops by the chip by decreasing the power, and we see that ultimately we're going to see something here. We're going to see that the optimum flop rate was done when we ran at the highest wattage, and we see the optimum flops per watt being obtained somewhere around 220 watts. So we're seeing an increase in terms of the efficiency by dropping the power, even for something like a matrix multiply. Now, when we look at doing the same operation through standard DRAM, using the DDR4 memory associated with that, we get a very similar kind of behavior associated with that. The performance is a little bit lower, but it's about the same. Matrix multiply has that reuse of data, so we're going to bring in data, get a lot of reuse of that data in the cache of the system itself, so we're not going to pay penalties of moving data back and forth, so we can actually see a pretty good situation because of the computationally intensive parts of that processor. If we're going to take a look now at matrix vectors, so matrix vector again has that characterization of not getting reuse of data. We read the matrix in basically and then dispose of it. We don't get to use it over again in the computation. And what we see in this case here at the nominal 260 watts is something around 84 gigaflops, a big drop in the performance over matrix. We see a flops per watt around 0.4 flops per watt associated with that. So that's just running matrix vector on the processor. We don't reach the thermal limits of the processor. We're really spending a lot of time moving data as opposed to using the floating point capabilities within this chip. And if we now go into a situation of reducing the power for the chip, we're going to look at how the performance is impacted for this. And what we see is that as we decrease the power for the chip, we see very little impact in terms of the overall performance that we're getting out of this. By reducing it to a certain point, we do see the performance drop in a very significant way, but we can maintain that and get about 20% reduction in power and still maintain the overall kind of performance. That's using MCDRAM, that's the fast memory. All the data is contained in that fast memory, and the best performance, the optimum performance is seen, of course, when we're running at that level, the optimum flop rate, and the optimum flops per watt is maintained over a course of the overall operations. And if we go to DDR4, that is using DDR4 as the primary place where the memory is, what we see is we can decrease the power cap. The frequency doesn't change. We're nowhere near any kind of thermal limits on this particular run. And we see that even though we can decrease the power to the chip, it maintains the same rate of execution, a very low rate of execution, around 25 gigaflops in this particular case. The achieved bandwidth is about 1/4 of what we see from MCDRAM. That's really the ratio between those two in terms of the overall performance. And we can get, again, this 20% savings by decreasing the power to the chip and not affecting the overall rate of execution that we see. Going to a vector operation, we have a much more intense memory usage, even more so than with matrix vector. This is doing a DAXB operation, AX plus Y. kind of operation of a vector. And we see performance that's around 35 gigaflops out of it. We see flops per watt of about 0.15, again, much lower than what we've seen before. And we can go through that same scenario of decreasing the power, and what we see here is it pretty much maintains the same kind of flops per watt ratio we see for decreasing the power, again by about 20%, that overall maintaining the kind of performance that we see out of that and affecting the frequency. When we go to DDR4 memory, again there's that bandwidth issue, a factor of 4 that we see in performance, which is a direct consequence of that. We're seeing the peak rates here of about 35, and here we see a peak rate of about 7 gigaflops, a factor of 5 in this particular case for doing these kind of vector operations. But we can reduce the power without impacting the performance for that operation by about 20%. And that would be something perhaps we can monitor within the code, adjust things, and get that 20% savings. We've been looking at applying these ideas to other applications. This is the HPCG benchmark. This is posed as an alternate to the other benchmark with that name associated with it. And that HPCG benchmark is an iterative algorithm solving a system of linear equations. And when we run that on this Knights Landing chip, we get something that looks like this in terms of the power that's consumed. If we reduce the power to the chip using the PAPI interface, we see basically the same kind of performance in terms of the time to solution. We can decrease it quite significantly, all the way down to about 40 watts without really seeing a noticeable change in terms of the performance. So this is an algorithm which is doing a lot of data movement. We can reduce the power, maintaining the same kind of performance within the processor itself. This is looking at DDR4 memory. Again, it's going to be a lot longer in terms of the time associated with it, and we see a similar kind of characteristic where we can reduce that power quite significantly down to around 140 watts and get the same kind of performance out of this implementation. So that's a good story. Looking at solving, this is solving a Helmholtz equation using a Jacobi kind of iteration to drive it. Again, we see we can do a drop in the power going to the chip without really having a substantial impact in terms of the time to solution for this problem, and that's especially true for going from DDR4 memory, so slow memory on this particular chip. So it's something which we're looking at aggressively and trying to see if we can set it and to monitor it in some way. This is Lattice-Boltzmann equation, solving it, and again, the same kind of thing where we can reduce overall power going to the chip without having a major impact in terms of the performance. And this is looking at a Monte Carlo simulation, the same kind of thing. Monte Carlo has a lot of data movements associated with it, yes?
You don't seem to have gigaflop rates on any of these.
Right, so I could do that clearly. We have all the information, but I thought it would be more interesting to reflect the power savings and the time to solution. So I'll just throw out a number. The gigaflop rate for HPCG. So this is a benchmark for doing it. And if I compare it with the peak performance, let's say the peak performance, the number we're looking at is something like 2% of peak performance. So the execution rate is really quite low because of the nature of the algorithm, doing a lot of data movement through that system. We have all the numbers and we can certainly generate those kind of things, but I think we would be disappointed if you were expecting high numbers. They're going to be very low in terms of the overall.
I wasn't expecting high numbers.
You were expecting? Excellent.
I want to show that we can do better.
Yes, I see. Okay, very good. Yes. Okay, so that's what we're pursuing. The other thing we're looking at is mixing precisions. So the idea here is to use a calculation that enjoys 64-bit accuracy, but does part of the computation in 32-bit arithmetic. And in doing something clever, perhaps, to recover the accuracy and building it back up to 64-bit. There's a number of algorithms that can do that. We can look at dense matrix algorithms, and also iterative algorithms have the ability to do this, perhaps using the preconditioner in short precision, 32-bit arithmetic, and then doing something with 64-bit as the outer iteration. And there's even greater interest today in processors that do 16-bit floating point arithmetic. You know, all the manufacturers have them. NVIDIA announced something just last week with tremendous potential performance out of a chip that does 16-bit floating point. They call it tensor arithmetic. It's being designed specifically for deep learning applications. And you know, we might as well look at to see what kind of things we could extract from that kind of a processor. They do 4x4 matrix multiplies very efficiently. Okay, so we're going to look at this algorithm. This is a mixed precision. We're going to look at this in terms of mixed precision. We want to solve a system of linear equations again, and we want to do it using a process called iterative refinement. So iterative refinement says we're going to factor a matrix into its LU components. We're going to solve a system of equations. If we did that in 64-bit arithmetic, we'd be done. If we want to correct the solution, though, we can carry on, and we carry on by computing a residual for the matrix, where that A has to be the original data, it can't be the factors. And then we go through an iterative process here where we compute a solution to the matrix with the right-hand side being the residual. And that vector Z is a correction to the solution that you've got. So this is really doing a correction to the solution that was computed in the previous step. And we can iterate on that until we get an accuracy that we're satisfied with. This is an old technique. It's been used for a number of years. In this context, if we look at the operation count, the LU factorization is the one that consumes n-cubed operations. Everything else is order n-squared operations. So that's a potentially good thing. And if I think about doing this LU factorization in single precision, I'm able to save quite a bit of time. Doing a single precision factorization is going to be at least a factor of 2 over the double precision factorization, and then I have to engage in some operations. Some are single, some are double precision, but the double precision things are always order n squared or order n operations. So I can engage in that without too much, consuming too much time. That's the attempt or the hope here. So this is, again, a well-known algorithm. It has a couple of issues. Number one, I have to have a copy of the original matrix. I have to have an original, so I have to have 2 copies of the matrix. One I use to factor, and another one I use to keep on the side to compute that residual. It has to be done with the original data. And that'll be done using double precision. So I have to have a copy of the matrix in single precision, which I factor, and a copy of the matrix in double precision, which I use just for this residual calculation. And if the matrix is too ill-conditioned, then I'm not going to be able to correct it. I'm not going to be able to get back the accuracy. And too ill-conditioned in this case is 8 digits. So if I lose 8 digits of accuracy because of the ill-conditioning, that implies that the ill-conditioning is 10 to the 8th. Then I'm not going to be able to recover any solution. But if I get even 1 digit right, then this process, this iteration here, will get me to the correct solution in a certain number of iterations. So let's see how it does. So this is a performance graph on Knight's Landing. This is double precision. The blue line is double precision. The green line is single precision, just solving them single and double. So single precision gets you a 32-bit answer. Double precision gets you a 64-bit answer. There's a factor of 2 there. That comes from the nature of floating point arithmetic and data movement and all the rest. So we haven't done anything special with that algorithm I just showed you. When we use that algorithm I showed you, we end up with a performance that looks like this. So this is the performance that we see, much closer to the single precision performance, much better than the double precision performance, getting the same accuracy as we got with the double precision. So that's a good story to tell, at least if the matrix is big enough. So you see the matrix size here has got to be greater than around 10,000 for it to make sense. And that's primarily because of that matrix vector operation. And on Knight's Landing, the performance for that matrix vector operation is so low, it can't recover enough to get back the performance. And these 2 things are pretty close anyway to begin with. Okay, so what does it do in terms of power? So this is the power that we see out of the single precision run. So we're monitoring now the power that's consumed. It consumes 1,175 joules to compute the solution, single precision solution. If I do it in double precision, it just about doubles. We get two 2,491 joules. This is all coming out of the PAPI tool that we're using to monitor what's going on inside the processor itself. And now when I use the iterative algorithm, one that does single precision factor and then refines it through that process, I end up with something that looks like this in terms of the overall time to solution and the overall performance that I see in terms of the amount of energy necessary to solve it. So instead of 2,490 joules, this thing's taking about 1,340 joules, a little bit more than half of the time. So it certainly is a reasonable thing to do. This is on a matrix of size 30,000. These matrices are well conditioned. It just takes a couple iterations to get back to the solution that I had. If the matrix was ill conditioned, then of course we'd see a different characteristic associated with that. Okay, so just coming to the conclusion of the talk here. So here are some critical issues that I see as we move towards exascale computing. These are things that we're trying to look at in the context of our library, numerical library that we're designing, but also it applies to other things as well. That is, these are the things which I think are the most important things to look after in terms of that. The first thing is reducing synchronization, coming up with algorithms that break that fork join loop level parallelism that we have in our models, trying to do things in a more asynchronous way, trying to look at a task-based model, trying to do things based on more event-driven kinds of computation, perhaps through a directed acyclic graph. The second thing is looking at communication reducing algorithms. So the idea here is communication is really the culprit in terms of impacting performance, and you want to come up with an algorithm that minimizes the communication, provably has a minimum for communication. My colleague at Berkeley, Jim Demmel, has sort of cornered the market in terms of algorithms for reducing or producing the minimum communication and then implementing them and, of course, getting a pretty good performance compared to the standard algorithms themselves. So that's the thing where we want to be in a position to really have the minimum kind of communication and overlap those communications with the computation. The second thing is trying to exploit that single double precision. We get an impact because of single precision is twice as fast and we're moving less data around in the system and we get a benefit ultimately because of that data movement. Looking at doing auto-tuning, the machines that we have today are terribly complex. We have to build into the software the ability to tune to the complexities and the dynamic nature of the behavior of the hardware. We're looking at doing this power monitoring through an auto-tuning thing where the user really doesn't have to be involved in the details of reducing the power supply to the chip. The software is going to monitor what's going on and then make those adjustments in a way that is built into the software and adapting to the overall nature of the hardware that's there in an effort to perhaps help reduce the cost. We're interested in coming up with algorithms that are fault tolerant. The statement by the Exascale computing program is they want to have one failure per week for the Exascale machine, and I think that's partially driven by having algorithms which can resist failure. The idea here is to detect process failure and transition past that in the algorithm through the software, and do that in a way where it works if we have a hard failure, but also if we have a soft failure. Detect the fact that you have a soft failure, you got the wrong results, a bit was flipped along the way, be able to detect that, recover from it in some way, and then carry on the computation. In the area of linear algebra, there's a number of algorithms that have been built or are being designed that do just that. They can recover from failures. Algorithm-based fault tolerant is certainly one. But if we take a look at that directed acyclic graph that we have for the implementation of the algorithm, and we think about storing parts of that DAG as we've executed it, we can actually go back if we have to and re-execute parts of that DAG if we have the information stored to carry on the computation in the presence perhaps of process failure. And the last item here, if it'll come up, is about reproducibility. So this is something that perhaps we've taken for granted. That is, we have this notion that things are deterministic. And if I run my program today with a certain set of data, and I run that same program on the same machine with the same data, I should get the same exact results. Well, that's not true. And it's not true because of collective communications. I can't predict the order at which things are going to come together. And if I can't get the order correct, I may have small round-off error differences between the two runs, between today and tomorrow, and that small round-off error can be magnified by ill conditioning, either in the problem itself or in the algorithm, if we have an ill-conditioned algorithm that we're using. So it can be magnified. So the question here is, can we design algorithms which can be reproduced, that can produce results that are reproducible? And the answer, of course, is yes, we can. And the question now is, how much does it cost to do that? So what's the cost associated with imposing an order at which things are computed and having that repeated? So that's an interesting area of work. So that's my take on Exascale today. Thank you for your attention. You know, this work comes with a number of people in collaboration. We're involved in the ECP project. I have collaborators at Berkeley, at Denver, who have participated. We have a close collaboration with the guys in France at INRIA, as well as David Keys out at KAUST in Saudi Arabia. And I have a set of colleagues who have helped with this project. NSF, of course, has been a great contributor to the overall funding, as well as the Department of Energy, and a number of companies have also contributed and perhaps benefited from the software that we've developed. So thank you for your attention, and I'd be happy to answer any questions that you might have. Yes.
So Jack, in your synchronization reducing algorithm, our experience is when you build these data flow graphs and use these task management systems, the underlying runtime and hardware is still box synchronous. So a lot of times we end up generating too small GPU kernels, or the small MPI paths and so on. So what do you see the general trend in the vendor software hardware? Are they going in the right direction, managing those small kernels and so on, or we need to begin to think about a different paradigm?
Because I get it wrong when I implement these things. It's a lot of effort to get the right parameters there. So we have to do some tuning to do that. And the tuning comes about with experience, and we want to build that experience into a tool that can auto-tune itself. So you want to have something which can tune the software. So there's a number of efforts today which try to do that. Try to automatically generate code based on the characteristics of the hardware, sometimes doing it before the performance, before the execution. We had a tool called Atlas, which generated the BLAS in an automatic fashion many years ago. FFTW is another example of that, and there's a whole collection of these tools that have been developed. We want to extend those things to really impact the runtime and be effective in terms of driving the runtime so that it can effectively use whatever resources are out there. I'm not saying we have all the answers, but I'm saying that's a path which I think is important that we need to go down and experiment with, and hopefully gain some insight in. There's a number of people here who are involved in these areas. Mary Hall sitting in the audience from Utah, and she's leading some efforts in terms of designing these kind of tools. But many people are looking at these things. It's a topical thing, and I think it's an important area that should be covered in terms of the research and computing research that goes on, but also in terms of its impact on the applications.
Yeah, hang on.
Oh, I'm Sorab Ismail-Bighi from Yale. Really interesting talk. I was kind of interested in the part about the power budget. And you had multiple plots showing that, as you turn down the maximum power the processor can use, things took longer, performance sometimes went up, gigaflops or what, but generally what I noticed was the total power consumed, went down a little bit, and then it came up. So I guess it means that the processor, when it's idle, is just churning, and the memory is just wasting power. This seems to be the way these things are designed, right? They just have a very high level of low metabolism when they're resting, if you like. I mean, is that your general observation, that if you wanted to get, a low energy budget, this hardware is really not designed that way?
Well, so I would say that there's a sweet spot that we have to look for in terms of what do we do to turn down the power so that we can maintain the same kind of efficiency or greater efficiency in terms of flops per watt. And in the graphs, just looking at them, there's a sweet spot there where we were getting a 20% savings. So you were able to save 20% of your power usage. You may not have the same time to solution, but you're saving some power associated with it and being able to do that. So that's in the nature of tuning. What can we do to impact? Part of this, in some sense, is maybe a dream that we can impact the hardware designers in the future and have them design things which build into the hardware this ability to adjust themselves automatically to what's going on on the chip itself.
I mean, here's what I'm talking
Yeah.
about. Let's say I'm willing to wait twice as long to run my calculation, but I'd like half the power.
Yes.
Energy use, that was nowhere on these plots.
It wasn't on these plots except
The hardware devices don't work like that.
that's true. Yeah, you're not going to get that kind of savings overall. That's you're going to get about 10 to 20%, but you're not going to get a factor of 2 today. That's correct. Yes, exactly right.
So Jack, when you were prognosticating about the future exascale machines, you talked about these heterogeneous nodes.
Yeah.
But the last part of your talk was on Knight's Landing, which is a very homogeneous node. So I was wondering, could you comment about how the results you got on Knight's Landing is going to apply to sort of current and future homogeneous or heterogeneous nodes?
Right. So it's critical that the runtime system be able to manage the tasks in a way that effectively uses the underlying hardware. We would envision the node to be heterogeneous, to have some kind of accelerator associated with some common processor there. And we want the runtime system, we want to be able to have tasks that the runtime system can manage in a way that can effectively do that. Now, we have results which I haven't shown for this package we have called Magma. So Magma is designed specifically for GPUs and associated with a commodity processor. So we think about a front end and a back end kind of mode in that context. In the broader sense, that would be the node, where we have a commodity processor and then we have an accelerator that can be tapped into. And we have experiments and we have designs of software which can effectively split the computation, these kinds of computations, so it can use both the accelerator part and the front end part, I'll call it, of the chip quite effectively, driving it at their peak rates. Now, of course, we're going to get more out of the accelerator, so you want to focus on the accelerator part of the computation, but you don't want to waste what's going on the front part as well. So we have implementations which do that. In our ultimate software for Exascale, we're going to rely a lot on the runtime system helping with that. And some of the signs from the runtime system are encouraging in terms of being able to accommodate that kind of scheduling across that kind of heterogeneous platform.
This is Gabor Tóth from University of Michigan. I'm interested in what computer languages are used in the projects and what languages are supported. So what kind of interfaces you give? Is it Fortran, C++, Python, and so on?
So you've named them. Well, Fortran, C++, Python are clearly the ones that we focus on today. I see people who want to use Julia as a language. It's a high-level language, sort of like MATLAB, only perhaps more efficient in terms of how it interfaces to the rest of the application. But those are the major things. We see features in OpenMP. The Chinese are using OpenACC to drive their accelerators on their chips. So I would say all of those things are important in the mix. I don't see any new languages having wide adoption for Exascale kinds of computations. That's not to say we shouldn't be interested in pursuing language research. We should be looking at things that perhaps can benefit large scientific computations, but today we don't have that.
We have time for one more question, if there's one.
So moving away from the Felipe Menanto, moving away from the University of Illinois, moving away from the Exascale world, there's still some processes that need to run on, on single cores, and they still need to do, all of these matrix operations. And you are either subjected to use MKL, or you need to go through the pains of trying to figure out that Atlas is gonna do all of the optimizations right. And you either pay to use MKL, or you're lucky that they work on the HPC machine they're using, or you have to go through the optimization of Atlas. Do you see there's a path forward for optimization on single cores when users want to run embarrassingly parallelized processes?
Let me just point out a couple things. MKL is free, I believe, today. So you don't have to pay for it any longer. So there's, at one point they were charging for it, and now it's just available. So that's.
Last time I checked, it's not.
Sorry, what?
Last time I checked, it was
Oh,
not.
I think it is. I think it is. So maybe at least it's intended to be free. So we'll look again. Okay. So what can a user do to optimize for single core performance on a given thing? So there are tools there to help in terms of understanding what's going on inside of your application. There's a large collection of tools that people have developed that can probe things and get a handle on what's going on. We have PAPI is a very low-level tool, but it plugs into other tools which can do the analysis in a very effective way. So guys in Oregon have a set of tools for doing that. The guys at Rice have a set of tools which are being used for applications to, again, monitor and try to uncover where the bottlenecks are. Once you know where the bottlenecks are, you can go after and try to extract performance. I have to say that you want to make sure you get the node performance right before you move on to looking at a larger ensemble of things. Because if your node performance is not good, the ensemble is not going to be very effective in terms of solving the problem. So make sure you got things correct at the low level, and then build on top of that at the other end. So getting it right at the core level is certainly in that direction, making sure that the things run very efficiently overall, and trying to extract as much performance as you can. But use what the if you can, use what the manufacturers provide, because they're usually pretty good, and sometimes people have things which are better, which later get incorporated into the manufacturer stuff. So we have a close interaction with the MKL team, and when we have monthly meetings, and when we uncover things, we quickly tell them that here's what you need to do to improve this routine. The next time the release comes out, they're matching our performance. So I showed a comparison here between MKL and our software. I can guarantee when the next release comes out, they're going to be equal to what we are, or if not better.
So before we break, I need to get your opinion. Did Jack meet the challenge? Yeah. I think we'll give him a mulligan at 2 minutes and 47 seconds, and that's the only one that he mentioned with that. So here is your bottle of Scotch, Jack. I hope you enjoy it.
I hope we enjoy it. Well, thank you so much. 14-year. Well, thank you.
I didn't think you could be able to do it. But also, Jack's from Tennessee. So they make a particular type of whiskey there that I don't know if he drinks, because I've only seen him drink Scotch. But there is bourbon from Bend, Oregon. So I figured he can take some of that home as well, since he has to check his luggage anyway. So thank you very much, Jack. That was great.
Slange.